December 10th, 1941. 3 days after Pearl Harbor, a convoy of American trucks rolls through the jungles of Malaya, racing to evacuate British civilians ahead of the advancing Japanese Imperial Army. Each truck rides on rubber tires, made from latex, harvested from plantations now less than 50 miles behind Japanese lines. The convoy commander, Captain James Richardson, doesn't know it yet, but within 3 months, 97% of the world's natural rubber supply will be under Japanese control. The tires his convoy rides on represent a resource that will become more valuable than gold, more critical than steel, and absolutely impossible to replace. Back in Washington, D.C., War Production Board analysts are already running the numbers. America needs 600,000 tons of rubber per year to fight a mechanized war. Existing stockpiles total 660,000 tons, barely enough for 13 months. After that, without natural rubber, the entire American war machine grinds to a halt. Tanks can't move without treads. Trucks can't deliver supplies without tires. Aircraft can't land without tires. Ships can't seal engine rooms without rubber gaskets. The Jeep alone, which will become the war's most essential vehicle, requires 32 pounds of rubber. With plans to build over 600,000 Jeeps, that's £9.6 million right there, not counting replacement tires. This is the documented story of how America lost access to 97% of the world's natural rubber in 1942, how the country faced total military collapse within months, and how American chemical engineers, led by companies like Goodyear, B.F., Goodrich, Firestone, and Standard Oil, invented synthetic rubber from petroleum and coal in time to save the war effort. It's a story about chemistry, desperation, and industrial mobilization on a scale the world had never seen. The rubber tree, Hevea brasiliensis, is native to the Amazon rainforest. For thousands of years, indigenous peoples tapped the trees for latex, the milky sap that contains rubber particles suspended in water. In 1839, American inventor Charles Goodyear discovered vulcanization, the process of heating rubber with sulfur to create a stable, durable material that didn't melt in summer heat or crack in winter cold. This discovery transformed rubber from a curiosity into an industrial material. By the early 1900s, demand for rubber exploded with the automobile industry. Henry Ford's Model T needed 4 tires, plus various hoses, belts, and seals. As car production increased, so did rubber consumption. But rubber trees only grow in tropical climates within 10 degrees of the equator, and they take 7 years to mature before producing latex. The Amazon could supply limited quantities, but planters needed vast new sources. In 1876, British explorer Henry Wickham smuggled 70,000 Hevea seeds out of Brazil in violation of Brazilian law. British botanists germinated 2,800 seedlings at Kew Gardens in London, then shipped them to British colonies in Southeast Asia. By 1900, British Malaya, modern-day Malaysia, had established successful rubber plantations. The Dutch followed in the Netherlands East Indies, modern Indonesia. By 1940, Southeast Asia produced 98% of the world's natural rubber. British Malaya alone produced 40% of global output. The Netherlands East Indies produced another 37%. British Ceylon, modern Sri Lanka, French Indochina, and Thailand supplied most of the remainder. Total American production from Liberia and limited Central American plantations was under 2% of U.S. needs. America imported 92% of its rubber from Southeast Asia and stockpiled only minimal reserves. This dependence on a single source region created enormous strategic vulnerability. If Japan, increasingly aggressive in the Pacific, captured Southeast Asian plantations, America would lose access to rubber almost overnight. Without rubber, modern mechanized warfare became impossible. Every military vehicle, every aircraft, every ship depended on rubber components. There were no substitutes for tires, no alternatives for sealing systems, no way to wage industrial war without vast quantities of rubber. American chemists knew this vulnerability existed. As early as 1910, scientists had been experimenting with synthetic rubber. German chemists during World War I had developed methyl rubber and other early synthetics when British naval blockades cut Germany off from colonial rubber supplies. These early synthetics were inferior to natural rubber, more expensive, and required chemicals Germany couldn't easily obtain. But they proved synthetic rubber was theoretically possible. In 1931, DuPont chemist Wallace Carruthers and his team developed neoprene, a synthetic rubber with superior oil and heat resistance. Neoprene worked excellently for specialized applications like oil hoses and electrical insulation, but it couldn't replace natural rubber for tires. The material was too expensive, and its properties didn't match natural rubber's unique combination of flexibility, strength, and durability. Standard Oil chemists working with German company IG Farben developed Buna rubber in the 1930 seconds. Buna, short for butadiene and natrium, German for sodium, used butadiene derived from petroleum and sodium as a polymerization catalyst. Buna S, polymerizing butadiene with styrene, showed promising tire-making properties. But Standard Oil's partnership with IG Farben created complications. When war came, the American government suspected Standard Oil of prioritizing German interests, and the Buna patents became tangled in investigations. By December 1941, America had small-scale synthetic rubber production capacity, maybe 8,000 tons per year, less than 2% of wartime needs. The technology existed in laboratories. The chemistry was understood. But nobody had built factories capable of producing hundreds of thousands of tons of synthetic rubber. Nobody had solved the engineering problems of scaling laboratory processes to industrial production. And nobody had the political will to invest billions in synthetic rubber plants while cheap natural rubber flowed from Malaya. Then Japan attacked Pearl Harbor. Within weeks, Japanese forces swept through Southeast Asia with terrifying speed. Hong Kong fell on December 25, 1941. Manila fell on January 2, 1942. Singapore, Britain's fortress city and centre of Malayan rubber production, surrendered on February 15, 1942. The Netherlands East Indies fell by March 9, 1942. In 3 months, Japan captured virtually every major rubber-producing region in the world. American rubber stockpiles, which had seemed adequate in peacetime, suddenly represented less than 1 year's wartime consumption. President Franklin Roosevelt declared rubber the #1 critical material shortage. On January 3, 1942, just weeks after Pearl Harbor, Roosevelt created the Rubber Reserve Company under the Reconstruction Finance Corporation. Jesse Jones, Federal Loan Administrator, became responsible for building America's synthetic rubber industry from scratch. The crisis was existential. Without rubber, the United States couldn't field a mechanized military. Tanks immobilized, trucks grounded, aircraft unable to land safely. The Jeep program, just beginning production, faced cancellation without tires. Liberty ship construction needed rubber for countless gaskets and seals. Every weapon system, every supply truck, every critical piece of equipment depended on rubber components. William Jeffers, president of Union Pacific Railroad, was appointed rubber director on September 15, 1942, with authority superseding even military priorities. His job was simple and impossible. Build enough synthetic rubber production to supply total American wartime needs within 2 years. The target: 800,000 tons per year. By the end of 1943. Nobody had ever built chemical plants on that scale. Nobody had proven synthetic rubber could match natural rubber's performance in military applications, and the chemistry required vast quantities of chemicals America wasn't producing in adequate volumes. Making synthetic rubber required 3 key inputs: butadiene, a chemical derived from petroleum or alcohol; styrene, derived from petroleum, and the knowledge to polymerize these chemicals into rubber-like materials. None existed in sufficient quantity in early 1942. Goodyear, B, F, Goodrich, Firestone, and U.S. Rubber, America's major tire companies, had all been experimenting with synthetics. Each company had developed slightly different processes. Goodyear favored Buna S, copolymerizing butadiene and styrene in ratios around 75% butadiene to 25% styrene. B. F. Goodrich had developed amarypol, similar in chemistry but using different catalysts and temperature controls. Competition between companies had slowed information sharing, but the war emergency forced cooperation. In June 1942, tire companies, oil companies, and chemical companies formed a pool of synthetic rubber patents. Companies agreed to share technical knowledge freely. Competitive advantages that companies had guarded for years suddenly became open information. Goodyear's emulsion polymerization process. B. F. Goodrich's cold rubber techniques, Standard Oil's catalyst formulations, all became available to any company willing to build synthetic rubber plants. The government committed unprecedented resources. In 1942 and 1943, the United States spent over $700 million, equivalent to roughly $12 billion in 2024 dollars, building synthetic rubber production capacity. 51 synthetic rubber plants were constructed across the country. 15 butadiene plants to produce the primary chemical feedstock. 8 styrene plants. 28 polymerization plants to combine butadiene and styrene into synthetic rubber. The construction timeline was extraordinary. The first major plant, Goodyear's facility in Akron, Ohio, broke ground in March 1942 and produced first rubber in April 1943. 13 months from dirt to production. Plants normally requiring 3 to 4 years of design and construction were built in 12 to 18 months. Engineers worked around the clock. Steel prioritization ensured reactor vessels, piping, and structures arrived on schedule. Labor disputes were suspended, strikes prohibited. The rubber program had absolute priority. But building plants was only half the problem. The plants needed feedstock. Butadiene came from petroleum through a cracking process that broke large hydrocarbon molecules into smaller ones. Pre-war, America produced almost no butadiene. Suddenly, the country needed 450,000 tons per year. Oil refineries had to be reconfigured, new cracking units built, processes optimized. By late 1942, butadiene production was ramping up, but not fast enough. Styrene, the other critical ingredient, presented similar challenges. Styrene is derived from benzene, which comes from petroleum or coal tar. Pre-war American styrene production was under 10,000 tons per year, almost entirely for polystyrene plastics. Synthetic rubber needed 100,000 tons of styrene per year. New styrene plants were built adjacent to refineries and coke plants that could supply benzene. As feedstock production increased, the polymerization plants came online. The chemistry was complex. Butadiene and styrene don't spontaneously combine into rubber. They require initiators, catalysts that start the polymerization reaction. They require careful temperature control. Too hot and the polymers degrade. Too cold and reaction rates drop to useless levels. They require emulsifiers, chemicals that keep the polymerizing rubber particles suspended in water. The resulting product, called GRS for government rubber styrene, wasn't identical to natural rubber. It was harder, less flexible when cold, more prone to heat buildup during use. Tire engineers had to reformulate tire designs. The same tire design that worked with natural rubber failed with GRS because heat buildup caused blowouts. Through trial and error, engineers learned to modify tread patterns, adjust rubber compounds, and change construction techniques to make GRS perform adequately. By the end of 1943, American synthetic rubber production reached 231,000 tons. Still short of the 800,000-ton target, but dramatically better than the 8,000 tons produced in 1941. Through 1944, production climbed rapidly. New plants came online. Existing plants optimized processes. By the end of 1944, production hit 753,000 tons. By the end of 1945, American synthetic rubber production exceeded 920,000 tons per year, finally surpassing the original target. The scale of this achievement is difficult to overstate. In less than 4 years, America built an entire synthetic rubber industry from essentially nothing. The 51 plants constructed represented one of the largest industrial construction programs in history. The chemical engineering knowledge developed during this crash program advanced the field by decades. Polymerization chemistry, catalyst development, process optimization, all leapt forward because thousands of chemists and engineers were working simultaneously on related problems. The impact on the war was decisive. By 1944, American military vehicles were running on synthetic tires that, while not quite as good as natural rubber, were good enough. Jeeps rolled off production lines with GRS tires. Trucks delivered supplies on GRS tires. Bombers landed on GRS tires. The shortage that threatened to strangle American war production in early 1942 had been solved by late 1944 through industrial mobilization and chemical innovation. Meanwhile, Japan's capture of Southeast Asian rubber plantations didn't provide the advantage Japanese planners had expected. While Japan controlled the rubber trees, they lacked the industrial capacity to utilize rubber effectively. Japanese factories couldn't match American production, even with access to natural rubber. Japanese vehicles were often low quality regardless of rubber availability. And American submarine warfare increasingly disrupted Japanese shipping, making it difficult to transport rubber from Southeast Asian plantations to Japanese factories. Germany faced even worse rubber shortages. Cut off from Southeast Asia and blockaded by Allied navies, Germany had no access to natural rubber after early in the war. German chemists produced Buna rubber using coal-derived chemicals, but production volumes were inadequate. By 1944, German military vehicles frequently used reclaimed rubber from old tires or solid rubber substitutes that wore quickly and rode poorly. German aircraft increasingly used wooden components to replace rubber parts. Tank production was sometimes delayed, waiting for rubber seals and gaskets. The irony is that Germany had pioneered synthetic rubber chemistry in World War I and had continued research through the 1930 seconds. IG Farben's Buna was technically more advanced than early American synthetic rubber. But Germany lacked petroleum resources to make synthetic rubber in large quantities. German Buna production depended on coal gasification, a slower and more expensive process. Germany also lacked the political will to invest in synthetic rubber plants on American scale until too late. By the time Germany recognized the critical shortage, Allied bombing had made constructing large chemical plants nearly impossible. Post-war, the synthetic rubber industry that America built for military necessity became the foundation for global synthetic rubber production. The GRS formulation developed during the war evolved into SBR, styrene butadiene rubber, which remains the most common synthetic rubber today. Modern automobile tires are typically 60% synthetic rubber, 30% natural rubber, 10% other materials. The synthetic portion is almost always SBR, descended directly from wartime GRS. The chemical plants built during the war continued operating. Some were sold to private companies. Goodyear bought several government plants, so did other tire companies. The government maintained strategic reserves but shifted production to private industry. By 1955, American synthetic rubber production exceeded natural rubber consumption. The dependence on Southeast Asian plantations that had nearly crippled America in 1942 was permanently broken. Modern synthetic rubber technology has advanced far beyond wartime GRS. Chemists have developed specialized synthetic rubbers for specific applications: butyl rubber for inner tubes and tire inner liners, EPDM rubber for weather stripping and roofing, silicone rubber for high-temperature applications, nitrile rubber for oil resistance, neoprene for chemical resistance. Each represents descendants of the wartime crash program that proved synthetic rubber could replace natural rubber. The environmental and economic consequences were significant. Natural rubber production requires tropical plantations, 7-year growing cycles, and labor-intensive tapping. Synthetic rubber can be made anywhere with petroleum refineries, responds immediately to demand changes, and requires less land. This shifted economic power from tropical rubber-growing regions to industrialized nations with petroleum resources and chemical industries. Southeast Asian rubber plantations still exist, and natural rubber remains important for specialized applications, where its unique properties, especially low heat buildup and high resilience, matter. Truck tires, aircraft tires, and off-road vehicle tires often use high natural rubber content, but the economic dominance Southeast Asia held in 1940 never returned. Synthetic rubber permanently changed the industry's economics. The Goodyear Tire and Rubber Company, founded in 1898 by Frank Seiberling and named after Charles Goodyear despite no business connection, became one of synthetic rubber's pioneers. Goodyear's Akron plants produced enormous quantities of GRS during the war. The company's chemical division developed improved synthetic formulations. Post-war, Goodyear became the world's largest tire company, a position held for decades. By the 1992, global tire industry consolidation changed the landscape. Japanese companies like Bridgestone acquired American firms. Bridgestone bought Firestone in 1988. Michelin of France acquired Uniroyal Goodrich in 1990. Goodyear remained independent, but faced intense competition. As of 2024, Goodyear is the third largest tire company globally, behind Bridgestone and Michelin, with over $20 billion in annual revenue and operations in 22 countries. F. Goodrich, another wartime synthetic rubber pioneer, had a different trajectory. The company sold its tire division to Michelin in 1988, retaining only its aerospace and chemical businesses. Today, Goodrich Corporation, now part of Raytheon Technologies, manufactures aircraft components, including landing gear, which still use synthetic rubber in tires and seals descended from wartime formulations. Firestone Tire and Rubber Company, founded in 1900 by Harvey Firestone, contributed significantly to synthetic rubber development. The company operated major synthetic rubber plants during the war. Post-war, Firestone remained a major tire manufacturer until quality problems in the 1970s damaged its reputation. Bridgestone acquired Firestone in 1988, and the brand continues as Bridgestone Firestone. Standard Oil, which had developed Buna rubber in partnership with IG Farben, faced controversy during the war. The Justice Department investigated whether Standard Oil had restricted American access to synthetic rubber technology to benefit German partners. Congressional hearings were contentious. Standard Oil executives testified that they had shared all relevant patents once war began, but suspicions persisted. The company's contribution to wartime butadiene production was nevertheless significant. Standard Oil refineries produced much of the petroleum-derived feedstock for synthetic rubber plants. The human dimension of the synthetic rubber program involved tens of thousands of workers, chemical engineers who designed plants, construction workers who built them in record time, chemical operators who ran continuous processes 24 hours a day, researchers who solved problems as they arose. None became famous. There were no dramatic battles, no heroic sacrifices, just relentless industrial effort. One story captures the scale. At the height of construction in 1943, over 60,000 construction workers were simultaneously building synthetic rubber plants across the country. In Port Neches, Texas, a butadiene plant employed 12,000 construction workers. In Institute, West Virginia, a styrene plant employed 8,000. In Louisville, Kentucky, a polymerization plant employed 6,000. These workers, many from rural areas with no chemical industry experience, were trained on the job and worked 6-day weeks, sometimes 7, to meet deadlines. The technical challenges they overcame were substantial. Butadiene is extremely flammable and tends to polymerize spontaneously if contaminated. Storage and handling required specialized equipment and procedures. Styrene has a distinctive, unpleasant odor and is also reactive. Polymerization reactions, if not carefully controlled, can run away, overheating, and potentially exploding. The safety record, given the scale and speed of construction, was remarkably good, though accidents did occur. The intellectual property complications were complex. Before the war, companies guarded synthetic rubber patents jealously. Standard Oil's agreements with IG Farben restricted American companies from using certain German-developed processes. American companies had their own patents covering different processes. When the government demanded cooperation, Companies had to abandon competitive advantages they'd spent millions developing. The solution was the Rubber Reserve Company's patent pool. Companies contributed patents to a common pool. Any company building synthetic rubber plants could use any patented process without licensing fees. In exchange, companies were guaranteed cost-plus contracts for rubber they produced. This arrangement worked because wartime demand was so enormous that no single company could meet it. Everyone's plants would run at full capacity regardless of competition. Post-war, the patent pool dissolved and companies resumed normal competitive behavior, but the knowledge couldn't be unlearned. Synthetic rubber chemistry was now widely understood. Hundreds of engineers had practical experience. Equipment suppliers knew how to build the necessary reactors and processing equipment. The industry that had been created under emergency conditions became permanent. The agricultural consequences were profound. In 1940, American farmers grew almost no soybeans. Soybeans contain oils useful for synthetic rubber production. By 1945, soybean acreage had expanded dramatically, providing oils for rubber and other chemical syntheses. This wartime expansion made soybeans a major American crop, reshaping agricultural economics. Alcohol production also increased. Some butadiene plants used alcohol derived from grain fermentation rather than petroleum. This created markets for grain that helped support farm prices during the war. Post-war, petroleum-derived butadiene proved cheaper and alcohol-based production declined, but the capability had been demonstrated. The strategic lesson was clear. Nations dependent on single-source critical materials are vulnerable. America in 1940 depended overwhelmingly on Southeast Asian natural rubber with no viable alternative. When that source disappeared, only massive industrial mobilization prevented disaster. After 1945, American strategic planning emphasized avoiding such dependencies. Stockpiles of critical materials were established. Domestic production of strategic materials was subsidized even when imports were cheaper. Synthetic alternatives were researched for materials without domestic sources. This lesson influenced Cold War industrial policy. When the United States faced potential shortages of chromium, cobalt, tungsten, or other strategic metals, programs were initiated to develop substitutes or secure alternative sources. The rubber crisis of 1942 became a case study in what happens when industrial powers depend on resources they don't control. The environmental costs of synthetic rubber production were significant, but not widely recognized until decades later. Butadiene and styrene production creates chemical wastes. Polymerization plants discharge water contaminated with trace chemicals. Synthetic rubber itself doesn't biodegrade. Tire dumps became environmental problems. Modern regulations have reduced but not eliminated these issues. The economic benefits were enormous. The synthetic rubber industry employed hundreds of thousands of workers. The chemical knowledge developed during the war led to entire new industries. Synthetic polymers, plastics, resins, all benefited from wartime advances in polymerization chemistry. The petrochemical industry that dominates modern chemical manufacturing descends directly from wartime synthetic rubber programs. Universities expanded chemical engineering programs to meet demand. MIT, Carnegie Tech, and other engineering schools trained thousands of chemical engineers during the war. Many continued in the industry post-war. Chemical engineering became one of the most important and lucrative engineering disciplines, directly traceable to wartime needs. The question of whether synthetic rubber was actually better than natural rubber depends on application. For most tire applications, modern synthetic rubber performs as well, or better, than natural rubber. It's more consistent in quality, responds to formulation changes more predictably, and costs less. For specialized applications like large aircraft tires or heavy truck tires where heat buildup is critical, natural rubber still has advantages. The reality is that modern tires use both. A typical passenger car tire might be 60% synthetic rubber, mostly SBR, providing wear resistance and wet traction. 30% natural rubber, providing flexibility and low heat buildup. 10% specialized synthetics, like butyl rubber, for the inner liner that holds air. This hybrid approach combines the best properties of each rubber type. The man who started it all, Charles Goodyear, died in 1860, decades before rubber became critical to modern industry. He spent much of his life in poverty despite inventing vulcanization, the process that made commercial rubber possible. Goodyear's discovery in 1839 transformed a curiosity into an industrial material, but he died owing more money than his patents ever earned. Frank Seiberling, who founded Goodyear Tire and Rubber Company in 1898 and named it after Charles Goodyear to honor his contribution, built a successful business. But Seiberling lost control of Goodyear during the 1920s in a financial dispute. He went on to found Seiberling Rubber Company, a smaller tire maker that continued operating until the 1962. Harvey Firestone, founder of Firestone Tire and Rubber, tried to avoid rubber dependency by establishing rubber plantations in Liberia during the 1920s. Firestone invested millions creating Harble, named after Harvey and his wife Ida Bell. The plantations produced rubber, but never achieved the scale needed to supply American needs. During World War II, Liberian rubber helped, but synthetic rubber made Firestone's plantation investment largely irrelevant. The geopolitical consequences extended beyond the war. Southeast Asian countries that had depended on rubber exports faced economic disruption when synthetic rubber reduced demand. Malaysia, Indonesia, Thailand, and Sri Lanka all had to diversify their economies. The plantation system that had dominated Southeast Asian agriculture declined. This contributed to post-war independence movements and economic restructuring. Japan's wartime capture of rubber-producing regions turned out to be less valuable than expected. Japanese industry couldn't utilize the rubber effectively. Synthetic rubber programs in Japan lagged American efforts. Japanese wartime economic planning proved less effective than American mobilization. By 1945, Japan's rubber situation was desperate regardless of plantation access, while America had more synthetic rubber than it needed. The ultimate irony of the synthetic rubber story is that the crisis was preventable. If American planners had recognized the vulnerability before 1940, synthetic rubber production could have been developed deliberately rather than frantically. The technology existed. The chemistry was known. What was missing was political will to invest in expensive synthetic plants while cheap natural rubber was available. Pearl Harbor and Japanese conquest of Southeast Asia created the crisis that forced action. Within 18 months of recognizing the emergency, America was producing synthetic rubber in meaningful quantities. Within 4 years, America had built enough capacity to supply total wartime needs plus reserves. The achievement was extraordinary, but it required a disaster to motivate the effort. This pattern, crisis followed by mobilization, appears repeatedly in American industrial history. The country often waits until emergencies force action, then responds with overwhelming resources and ingenuity. During peacetime, inefficiency and short-term thinking dominate. During wartime, focus and determination solve problems that seemed impossible. The synthetic rubber program exemplified this pattern. Tire companies had experimented with synthetics since the 1920s, but never commercialized them because natural rubber was cheaper. Oil companies had developed butadiene production processes, but built no plants because demand didn't exist. Chemical companies had studied polymerization, but saw no market for large-scale production. Each company, acting rationally in response to market conditions, created no synthetic rubber industry. The government, acting in response to national emergency, built the industry in 4 years through massive investment, forced cooperation, and absolute priority. The result was an industry that continued operating profitably for decades after the emergency ended. Sometimes markets fail to provide what national security requires. World War II demonstrated that government action, when necessary and well executed, can create industries that markets won't. Today, the synthetic rubber industry that saved America in 1942 is global, competitive, and technologically advanced. Annual world synthetic rubber production exceeds 15 million tons. SBR, the descendant of wartime GRS, remains the largest volume synthetic rubber at about 6 million tons per year. polybutadiene rubber, developed post-war, produces about 3 million tons per year. Styrene butadiene, EPDM, nitrile, and specialty rubbers make up the remainder. The chemistry has evolved. Modern catalysts produce polymers with more controlled structures. Polymerization processes are cleaner and more efficient. Quality control is far superior. But the fundamental chemistry, butadiene plus styrene, polymerized into rubber-like materials, remains essentially what Goodyear, BF, Goodrich and Standard Oil developed under wartime pressure in 1942 and 1943. The factories in Akron, Port Neches, Institute, and Louisville that produced wartime synthetic rubber have mostly closed or been repurposed. The American tire industry, once centered in Akron, has largely moved overseas or been acquired by foreign companies. But the knowledge created during the war, the chemical engineering expertise, the polymerization chemistry, the process design, all that remains. Chemical engineers today study wartime synthetic rubber programs as examples of rapid industrial scale-up. How do you go from laboratory to full production in 18 months? How do you build 51 plants simultaneously? How do you solve technical problems as they arise when there's no time for extended research? The answers, documented in wartime reports and technical papers, inform modern chemical engineering practice. The rubber crisis of 1942 taught America that strategic independence requires more than military strength. It requires industrial capacity, technical knowledge, and willingness to invest in alternatives to imported materials. These lessons shaped Cold War policies and continue influencing American strategic thinking today. When historians discuss World War II's industrial achievements, synthetic rubber often receives less attention than aircraft production, shipbuilding, or the Manhattan Project. But in terms of sheer economic scale and technical difficulty, the synthetic rubber program ranks among the greatest industrial accomplishments of the war. It took an industry that barely existed and scaled it to produce nearly 1 million tons per year in under 4 years. And unlike the Manhattan Project, which produced weapons used twice, synthetic rubber production continues today, 8 decades later, using chemistry developed under wartime pressure. The next time you drive on modern tires, realize that the rubber likely contains synthetic materials descended from the wartime crash program that saved America when Japan captured 97% of the world's natural rubber supply. The chemists and engineers who solved that crisis worked in obscurity. No monuments honor them. No dramatic photographs captured their achievements. But they built an industry from scratch under impossible deadlines and saved American war production from collapse. That's worth remembering. Because when crisis comes, as it inevitably does, America's response depends on having people who can solve impossible problems under terrible pressure. The synthetic rubber program proved such people exist. The question is whether the country will recognize the next crisis before disaster forces action, or whether, once again, catastrophe will be required to motivate achievement.